2018 exam, and there was kind of a surprise on that exam. They gave something called the they had a triangular rod shown above, has length L, mass M, and a non-uniform linear mass density given by the equation alpha equals 2mL squared times x. All right, so you had this thing, and linear mass density. Well, that's weird. What is linear mass density? Let's see if we can figure that out. And it's alpha was the linear mass density. It had 2 times the mass, so this is gonna, and units are really gonna help us out here. So let's take a look what we got here. We got kilograms, right, divided by meters squared times meters. So this is gonna be kilograms per meter, right? So this tells us wherever you are at that position, it's going to be so many kilograms per meter. You just multiply it by how many meters you have, and you'll have how many kilograms. And it kind of makes sense that it looks like this because you could see that it's a triangle. So the mass goes up, the linear mass density goes up with distance. All right, so that is it, and this was. They set this up and they said x equals 0, and here x equals L. All right, so we need to find the moment of inertia of this rotated from one end of the rod. All right, so we want to find, using integral calculus, show the rotational inertia of the rod about its left end is ml squared over 2. Well, the good news is if you couldn't figure it out, they gave you the answer. So anyways, let's figure this out. We're gonna do this about the end, so we want to go like this. So we got something like that. All right, and we're gonna have these little slices. That's gonna be dm. Right, that's a little sliver of mass. That's gonna be position x. And all right, so let's take a look. The moment of inertia is, in general, it's going to be r squared dm. All right, so we just need to get that dm out of there. We really want this in terms of dx. So let's take a look. Let's go like this. This little mass, what is it? How much mass is in there? Well, if we knew the linear density, which is 2m, this will give us the density at position x, right? So this will give us number of kilograms per meter. I just need to multiply how many meters this is wide, and I get the mass. I'll get that little mass. Well, how many meters is this? How wide is this? Well, it's dx wide is what it is, right? So dm equals the mass density times dx, right? And let's see if the units work out. I got kilograms, meters times meters. That's meters squared divided by meters squared. Yeah, the units work out. That looks good. This is the linear density. This tells us how many kilograms per meter at this position. And this gives us how many meters we have, dx meters. All right. So what do we got? We got moment of inertia equals. I'm going to replace r with x squared times a dm, which is 2m L squared x dx. And x goes from 0 to L, right? That's L right there. And what do we got? I'm going to bring out the 2m over L squared. And we just have x cubed dx from 0 to L. And so this is going to be 2ml squared x to the 4th over 4, 0 to L. There we go. We got that. All right. So that's going to be, we're going to end up with 2ml to the 4th divided by L squared over 4. Boy, I'm not writing too well today. L squared over 4. L squared goes away, and this becomes L squared. And that's, what do we got? ML squared over 2. And that is a moment of inertia of a rod about skinny end. Skinny end. About the skinny end. How do you spell skinny? Yeah, I think so. I don't know. All right. Oh, and that's what we wanted. Oh, good. Beauty. Nailed it. All right. And then they said the thin hoop shown above in figure 1 has mass M and radius L. Interesting. Radius L. And a rotational inertia about its center is ml squared. Well, of course it is. It's a hoop. The three rods identical to the rod in part A, how convenient, are now fastened to the thin hoop as shown in the figure above. Derive an expression for the rotational inertia of the hoop rod system about the center of the hoop. Express your answer in terms of M, L, and physical time. All right, so we got this thing, and we're going to rotate it about its center. And it's got 3 of these, right? It's got 1, 2, and 3 of these. And each one of these has a moment of inertia. What did we say it was? ml squared over 2. ml squared over 2. All right. So the moment of inertia total, about the center, equals 3 times I of the rods, right, about their end, plus I of the hoop, right? Each one of these added up some inertia, so that's what we got. That's I total. 3 times ml squared over 2 plus ml squared. So I guess this is L right here. That's L. All right, so what do we got? We got 3 halves ml squared plus ml squared. I guess, is that 5 halves ml squared? 5 halves ml squared is the total moment of inertia about the center, right? I think that's the answer. That looks right to me. There we go. So there we go. We just moment of inertia. Remember, moment of inertia is just a summation, right? Moment of inertia is we're just going to add up all the little pieces of mass and multiply it by how far they are from the point of rotation. Or, that's if you got pieces. And this is what we had. We had pieces. We had the hoop and we had 3 rods. So we're adding up pieces. Or if you have an extended object, like these were extended objects and we did that. These are the same thing. This is when you have like a finite large things that you add together, and this is infinite little molecules and stuff like that. All right. So I guess probably need that. And can't remember what they're going to ask next. So I'm probably going to need that. That's I total. About the center. All right. Any questions? Good. The hoop rod system is initially at rest and is held in place, but is free to rotate about its center. Okay, so I guess we got an axle going there. A constant force F is exerted tangent to the hoop for a time delta t. All right, so we got our. Let's draw that again, and we're gonna apply a force tangent to the edge of the hoop. There we go, and we got our 3. I'm not gonna draw them as triangles. I just do it like that. Just makes the drawing easier. We got something like that, and all right. So force times delta t. All right, I bet we're gonna calculate a torque. All right, so it looks like we can figure out the net torque on this, and then if you know the net torque, you can figure out the acceleration. Angular acceleration anyways. And if we know the angular acceleration, we can use the circular kinematics equations to find how fast it's going later. Drive an expression for the angular speed of the hoop rod system. All right, so we could sum the torques, which is going to be easy, is I alpha. All right, we know I. We can figure out the torque. That's easy enough because these are all L. And then I think we can use omega 1 equals omega 0 plus alpha delta t. Yeah, we could do that. They gave us that. We can calculate that. This is 0. All right, that's pretty easy, actually. All right, well, let's see what we got. Torque. The way I drew it, that is although they didn't specify the direction, that is a negative torque the way I had that. That is FL, negative FL, equals the moment of inertia, which is 5/2 ml squared times alpha. All right, let's solve for alpha. We can do that, and we end up with minus 2/5 ml equals alpha. Let's see. Oh, forgot my F. Can't forget my F. Let's see, are the units working out okay? We got F, which is kilogram meters per second squared, divided by mass, which is kilograms, and length, which is meters. All right, so meters go away, kilogram. We got 1/second squared. Yes, that is. The units are right, so we can feel pretty good about that, I guess. Let's plug that into here. We know that omega, this is 0. It said it started from rest. Omega 1 equals 2/5 F ml. I'm dropping the negative just because they didn't specify direction. That's the ways of my drawing. But in the answer, we're just going to give the magnitude because they didn't give any information about direction. So what do we got? 2/5 ml delta t. All right. Guess that's the answer. Huh. All right. Hopefully that's right. If it's not, well, I don't know. Talk to someone who knows how to do it right, and then you'll be able to figure it out. Let's see. Then that little wheel that we just built is rolling without slipping. Oh, rolling without slipping along a level horizontal surface with angular speed omega found in part C. At time t equals 0, the system begins rolling without slipping up a ramp as shown in the figure above. All right. On the figure of the hoop rod system, draw and label the forces, not components, that act on the system. Each force must be represented by a distinct arrow at and pointing away from the point. All right, so we got our wheel. I'm not even going to draw the spokes. We don't need no stinking spokes. So let's draw our forces here. Let's see, it looks like we got ourselves a normal force like that. And we got some, let's see, it's rolling up like that. So which way is friction acting? It's spinning, and I think friction is acting this way. And I believe it's static because it's rolling without friction. And then in the center we have the weight down like that. And that's our angle theta, which... I didn't give it. They didn't give us a theta. All right. So anyways, those are the forces. We got the normal force acting at the surface. We got friction like this. Now, why is friction that way? Well, this thing is rolling that way, right? It's spinning that way. And it's actually propelling it up. It's actually the rotation that's really kind of propelling it up the thing. And so it's spinning like this. It's applying a frictional force back on the surface that way, and the surface is applying a frictional force up. All right, justify your choice. Oh, okay. Well, all right. You got to justify each of these. Well, the normal force is just the surface pushing perpendicular to it. So this force right here is perpendicular to the surface. Weight is always straight down towards the center of the Earth. That's a force due to gravity. I guess I could call it the force due to gravity. That's the weight. And all right, so friction is up the ramp because as this thing's spinning, it's actually pushing back on the ramp, and the ramp is pushing it up. And actually, that friction is part of why it's going up the ramp. Part of it is just because it had a momentum with a component this way. So there's a component that way. But friction is actually helping to propel it up the ramp. Derive an expression for the change in height in the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches the maximum height. Express your answer in terms of M, L, I total, omega, and physical constants as appropriate. All right. So omega is that's the speed at the bottom. All right. So omega is, that's our omega. That's omega right there. All right. So this is going to be a conservation of energy problem. It starts at the bottom right here at 0 and goes to some height here, 1. All right. So we're going to use conservation of energy. Energy at 0 equals energy at 1. So initially this thing's rolling and it's going omega. Actually at this point, let's say this is stopped here. So omega equals 0 when it gets to here. And it also has a translational velocity. I'm going to call it 0. So what do we got? We got K0 trans plus K0 rotational equals gravitational potential energy at 1. So I got to define 0. I'm going to call this 0 gravitational potential energy at the bottom of the ramp. So when it gets to the top of the ramp, it's not moving. At its maximum height, it's only going to have gravitational potential energy. So here we go. We got 1/2 mv0 squared plus 1/2 I omega 0 squared equals mg, I'll call that h. They also said we need one more piece of information. They said it was rolling without slipping. That's a beautiful thing. That means that V equals omega R. In general, V equals omega R. So the translational speed equals omega R. But in this case, V equals omega L because R is called L in this particular problem. Let's substitute in some specific values. The mass of this thing is, each one of those was mass M, right? Yeah, mass M, and the hoop was mass M. So is that 4M V0 squared plus 1/2 I omega 0 squared equals, and this is that big M again. This is not the generic M. This is MGH, so that would be what? 4M GH1, because that had a mass M, and then you had the 3 hoop. They all had mass M's, right? Let's see, was that right? Yeah. Okay. And then I needed to use this idea that V equals omega L. So I end up with 4 over 2. 4 over 2 is 2. M omega 0 squared L squared plus 1/2 I omega 0 squared equals 4 MGH1. All right, well, this is kind of easy because we can leave this as I, and we didn't even need to substitute in omega that we calculated before. I don't know why we did that if we didn't substitute it in. But anyways, that's cool. So it makes our life easier with the algebra anyway. Omega 0 squared. I'm going to factor that out, and we're going to have 2ml squared plus I over 2 omega, oops, I over 2, right? All divided by 4mg equals h1. That's kind of nasty. Let's simplify that a little bit. Let's multiply top and bottom by 2. Omega 0 squared times 4ml squared plus I all over 8mg equals h1. All right. And they call that I total. Didn't need to substitute that in. Didn't need to substitute that in. We certainly could. It would have gotten messier. We would have substituted that and there. But they said we could do it in terms of omega and I total. So that's, there we go. Guess that's the answer for E. All right.
History. Physics.